Here we talk about shifting graphs of functions. Given the graph of a function, then if you take the function f of x minus h, all that plus k, has a graph that is the previous graph shifted left, right, up, or down. For example, y equals absolute value of x, that's this V-shaped graph. If you make it y equals absolute value of x plus k, that shifts the graph up or down. So here's y equals absolute value of x. Y equals absolute value of x plus 1 is shifted up by 1. Y equals absolute value of x plus 2 is shifted up 2. Y equals absolute value of x minus 1 is shifted down 1. Y equals absolute value of x minus 2 is shifted down 2. So y equals f of x, that plus k, shifts the graph up k units if k is positive, down if k is negative, or down absolute value if k is negative. Y equals absolute value of x minus h, so we have a minus h inside the absolute value sign. It shifts the graph left or right. Here's a graph of y equals absolute value of x. Y equals absolute value of x plus 1 is shifted to the right 1. Notice I have a minus 1 here, but it's shifted right 1. This minus 1 delays the graph. Y equals absolute value of x minus 2 delays it by 2 units. So it's shifted to the right 2 units. Y equals absolute value of x plus 1 is 1 unit earlier, so it's shifted left 1. Y equals absolute value of x plus 2 is shifted left 2 units. It's 2 units earlier. So y equals absolute value of the quantity x minus h shifts the graph right 8 units if h is positive. So if you do both, y equals f of x minus h, that plus k, that shifts the graphs right 8 units and up k units if h and k are positive. Note that there's slightly different behavior for inside and outside the function. Minus a positive number shifts it right, plus a positive number outside the function shifts it up. And often you'll get things like this. Absolute value of x plus 1, you have to write that as x minus negative 1. And so, it would be 1 unit to the left. So if this is the graph of y equals f of x, then y equals f of x minus h plus k is shifted over to the right h and up k. Then there's multiplying the function. A times f of x. And then next we'll be doing f of bx inside the function. But a times outside f of x. It stretches or squeezes or shifts the graph, flips the graph vertically. If a is positive, that's a vertical stretch. That makes it taller. Excuse me. So for example, if this is f of x, 2f of x is twice as tall. If a between 0 and 1 is a vertical squeeze, it makes it shorter. So a half f of x is a shorter graph than that. And if a is negative, that flips up or down. So if here it's f of x going up, then down, and up. Negative f of x goes down, then up, then down. Now, you can call this a times outside f of x. Modulates, like it controls the amplitude, how high or short the graph is. Now, any of you heard of amplitude modulation? Surely you've heard of that. No one? Everyone?
Nope.
Oh, sure. You've never heard of amplitude modulation radio? AM radio.
We're too young for that.
It still exists. Oh, well. All right. Oh, God.
I've heard of AM radio. I just didn't know what it was spelled out.
Yeah, it means amplitude modulation. The idea is the radio wave coming out of the oh, just a second. Okay, some people are chatting. Okay, I'll get to that later. The radio wave coming out of the radio tower has a certain frequency and amplitude, and the amplitude goes up and down and up and down in accordance with the wave that is the announcer's voice. The trouble with AM radio is at these moments where it's where the amplitude is low, the amplitude of the radio wave is low, and therefore this part of the signal can be interfered with by random electrical noise, someone running their lawnmower, a lightning strike, this, that, the other. So, all right. So AM radio is good for It's good for signals that can be low quality, such as voice or something as old-fashioned as Morse code. And yes, it exists too, and so on. Here, y equals f of bx. This stretches, squeezes, or flips the graph horizontally. Now, just as before, doing the operation inside the function has an opposite effect from doing it outside. Here, if a is bigger than 1, that makes it taller. Here, if b is bigger than 1, that makes it squeezed. It makes it faster. If b is between 0 and 1, that's a horizontal stretch. So
That's just a different label for the variable, right? B in this case.
no, b is a number, like 2x or whatever. X is.
Oh, I see. Gotcha. Differently defined. Okay.
Okay, fine. Yes, I know. In computer science, if words are variables, algebra is more old-fashioned, as you might expect. And b less than 0 flips left for right. So if here's the graph of f of x, f of 2x is the same graph, only squeezed inwards like this. And y equals f of a half x is stretched outwards like this. But it has the same amplitude. And y equals f of negative x flips left for right like this. So here, if y equals f of bx, the b modulates the frequency. Now, okay, I'm sure you've heard, I hope you've heard of frequency modulation, right? Frequency modulation is the F and M in FM radio. That still exists, doesn't it? Never mind. And the idea is that the radio wave off, the wave coming off the radio tower gets quicker and slower and quicker again in accordance with the voice or music signal that it's transmitting. Here, it's never at a low amplitude, and so it is less liable to be interfered with by random electrical noise. The problem here is that this no longer occupies a single frequency. It occupies a range of frequencies. And so you have to have a part of a radio band. And so they sell off or lease or whatever segments of the radio frequency spectrum for music players. So yeah, and so this gives a higher quality signal, which is why you find all the music stations are on FM radio. If this is the graph of y equals f of x, then y equals negative f of x flips up for down like that. Here's f of negative x, which flips left for right like that. And if you do both, y equals negative f of negative x, well, that flips it left for right and up for down, and that's the same as a 180-degree turn. It's a rotation around the origin. So, some examples. Graph y equals x minus 3 squared. Well, x squared is this U-shaped curve. And then x minus 3 squared, you mean you move it right and you get this U-shaped curve which touches down at 3 by 0 instead of 0 by 0. Graph 1 over x plus 4. 1 over x is this hyperbolic graph. And plus 4 outside the function means you lift it 4 units. So the graph looks like this. It's asymptotic to y equals 4, rather than here where y equals 0 is the asymptote. Here we have a couple of changes. Minus x minus 2 quantity cubed. X cubed is this n-shaped graph. If you use this minus, flip it up or down, then y equals negative x cubed is this S-shaped graph. And then if we move right 2, you get this graph here, this n-shaped graph going through 2 by 0 for this graph, to graph this function. All right, here we're given a function going through negative 5 by 0, negative 2 by 3. I guess I should include 0 by 0, 2 by negative 3, and 5 by 0. Graph f of negative x plus 3, and B graph minus twice f of x plus 3. Okay. For A, f of negative x, we flip left for right. So instead of this N-shaped graph, you get this S-shaped graph. That plus 3 moves it up 3, and it looks like this. Negative 2f of x. Well, this negative 2f of x first flips up for down and then stretches it vertically. So you get this very tall N-shaped graph. Then plus 3 moves it up 3, and you get this graph here, lifted 3 units. Well, I believe we're done with this for now.